Speaker. So today's speaker is one of my favorite people, a very good friend of the Michigan Math Department, a very good friend of the Michigan Math Corps at U of M. This is Coach Steve from Math Corps and from Williams College, who is going to tell us about, from the Manhattan Project to number theory, how nuclear physics helps us understand primes. And in fact, if you stick around after the talk, Coach Steve is an expert on REU programs, or research experiences for undergraduates, and he has graciously agreed to stick around and talk to us about REUs and applying for REUs and what they are and how do you apply and how do you know if it's right for you. David Spire, who is a faculty member here at U of M, is also going to stop by and participate. He is running the Michigan REU. He's in charge of that, so the one that's here at U of M. Okay, so stick around after the talk for that. And Coach Steve, take it away.
So thank you. It is always a pleasure to be here virtually, not as much as being there actually. I'm disabling my video because the Wi-Fi connection in my house is not so good. So I've just put up the links over here to the Williams Small REU Research Experience for Undergraduates, as well as a new one, the Polymath Junior, which we created last year. And it is a very different program, and I will talk about that at the end of the research talk today. Most of this work is joint with students. Only, I think, one person other than myself is actually a professor at the time any of this work was being done. I will try to specify when Michigan students were involved, either as undergraduates or graduate students. I have had the fortune of working with a tremendous number of Wolverines over the years, so I do apologize for those of you who have worked with me whose work is not being mentioned in this. 50 minutes is not nearly enough time for all of that stuff. And some of my students are kind enough to stick around, so if you have questions about REUs, some of them will be here at 5 o'clock as well. All right, so let me describe the fundamental problems. My wife, who's a professor of marketing, she also looks at this, but from a very different perspective, spacings between events. So you're studying some system, you observe some values T1, T2, T3, and the question is, what rules govern the spacings between the events? So for my wife, as a professor of marketing, she studies wait times. She might study things such as Disneyland, which does a phenomenal job of managing the waits of people in line. And so the question is, can you come up with rules that describe the behavior, the distribution? And there's a lot of different systems you can look at. And so today we're going to focus on three that look very different at first: energy levels of heavy nuclei, eigenvalues of matrices, and zeros of L functions. And again, this is just the tip of the iceberg in terms of what you can look at. And so when we're studying statistics, there are often three key steps in order to be able to get a good answer at the end of the day. The first is to determine the correct scale to study the events. So if we want to study the distribution of heights and we measure everything in miles, everything is going to be essentially zero and everything would be clumped together. So we want to find a good scale to spread things out a little bit. The next is, unfortunately in life, you typically can't look at what you want. So we try to find what's called an explicit formula relating what we want to study to something we can understand. And then the last one is that typically it is hard to study in mathematics a specific item, that the best chance we have is often to embed it in a family and do some kind of averaging. So if you're familiar with the central limit theorem, that's a great motivating example to keep in mind in what's going on. Okay, it is not always trivial to figure out what the correct statistic is to study. In one of the objects in L functions, if you talk to one professor, it took 6 months. If you postdoc working with him, it took 9 months to come up with what was the thing to look at that would be computationally feasible. So as I know everybody is coming from a variety of different backgrounds, I want to just spend a few slides in the beginning setting the stage of what math do we need. So for the most part, we just need linear algebra and some basic probability to do a lot of these calculations. Now, if you know more math, that is wonderful. And we will see later in the talk, in certain settings, some really nice mathematics comes to play. But many of these questions can be done with just basic linear algebra and a little bit of probability. So we say a non-zero vector is an eigenvector of matrix A with eigenvalue lambda if A acting on V gives you lambda times V. So a vector has magnitude and direction, and typically if you apply a matrix to a vector, you're going to change the direction. If you don't change the direction, we call it an eigenvector. It turns out eigenvectors are tremendously useful. One of the reasons is you can keep applying your matrix again and again and again, and it's very easy to figure out what happens if I apply it 10 times. It's just lambda to the 10th of V. So as an example, if I give you the matrix 1, 2, 2, 1, it turns out I can find a orthonormal basis, two vectors, this is an orthogonal basis, two vectors that are perpendicular, and they're both eigenvectors. So when I act on 1, 1, I get 3 times 1, 1. When I act on 1, negative 1, I get negative 1 times 1, 1. And there's a whole theory behind how you find them. What are the eigenvalues? I'm not going to get into that today, but it's an absolutely beautiful theory. The next thing I need is a little basics from probability. So we say x is a random variable with probability density p of x if the following three things hold. So this is going to be a continuous case. You could, of course, do a discrete case like rolling a die. P of x is non-negative. The integral from minus infinity to infinity of p of x equals 1. And the probability you take on a value between a and b is just the area under the curve from a to b. So if you've taken a calculus class and you've done integration and they haven't mentioned probability, you have a right to ask for a refund. This is one of the main reasons we love calculus, is it allows us to calculate probabilities of events. So there's a lot of different probability distributions you can look at. The exponential, the normal, and the uniform are three very important ones. For a lot of things, it doesn't really depend too much on the shape of the distribution, which is very nice. But these are three big ones that occur in a lot of places. All right, so a couple of key concepts. Anybody who has taken and is concerned about grades knows about the mean, the average value. So we just integrate x times the probability it happens. You can talk about how spread out something is the variance, so it's x minus mu squared. So the larger the variance is, the more spread out things are. The kth moment is just integrating x to the k against p of x. And a really nice observation is that, very similar to how a nice function is described by its Taylor series, a nice probability density is determined by its moments. So if you know the Taylor coefficients, you should hopefully know the function. If you know the moments, you should hopefully know the probability. This is not entirely true. There are a lot of technical conditions you need. Complex analysis is a great class to give you the technical conditions. But as a rule of thumb, the hope is that if we know the moments, we know the distribution. So what I want to do now is I want to talk a little bit about classical random matrix theory. So I like to bill myself as one of the last nuclear physicists to migrate over from nuclear physics to number theory. When I was an undergraduate at Yale back in the 90s, my mentor was a nuclear physicist. And he was one of the original experimenters in the 1950s who was collecting the data. And it was extremely hard to get this data. And 40 years later, it was still hard to get the data. And he became interested in number theory because you could simulate billions, you could calculate billions of the objects in number theory in days to weeks, whereas in years of measurements, they only had on the order of 1,000 data points. So I learned my number theory not from a number theory class, but from a nuclear physicist. So if you think my Boston accent is bad, my number theory accent could be a little bit harder to understand because I really do think about this in terms of nuclear physics. And at the end of the talk today, I will tell you how to interpret a lot of number theory from the perspective of nuclear physics. All right, so I'm not going to assume any familiarity with physics. I'm going to just quickly review a couple of things. So if I give you 1 point mass in the universe and nothing else, the universe is quite boring. If I give you 2 point masses and gravity and nothing else, we know how to solve it. As soon as I give you 3 point masses in general configuration, we can no longer write down a closed form solution. Well, if we can't even do 3 bodies, imagine something like uranium with over 200 protons and neutrons in the nucleus. How are we going to describe something like that? And so one idea is to shoot high-energy neutrons into the nucleus and see what comes out. So one of my favorite quotes in physics is, imagine you want to understand how a grandfather clock works. So what you do is you take 2 grandfather clocks, you accelerate them to about 99% of the speed of light, smash them together, and you look at all the stuff that comes out. And from that, you try to deduce how the grandfather clock works. Amazingly, this is one of the best methods we have of understanding what's going on at the subatomic scale. And there is an analog of this in number theory. There is an analog of sending high energy neutrons to figuring out what's going on with the primes. And so we will talk about that at the end. So if you've taken quantum mechanics quantum mechanics can often be formulated as the following matrix equation. So H is a matrix, its entries depend on the system, En are the energy levels, and Cn are the energy eigenfunctions. And so you basically have to solve the eigenvalue problem. Now, unfortunately, this is a little bit harder than the eigenvalue problem that you would typically do in a linear algebra class. The first reason that makes it harder is H is infinite by infinite. And most of the time we don't do matrices that big. The second and more severe is we don't know any of the entries. The system is so complex, we can't write down any of the entries, yet we somehow have to solve the equation. So, challenging. So, Eugene Wigner, who has a beautiful article on the unbelievable effectiveness of mathematics. So he was a physicist, did a lot of great work in mathematical physics, and talked about why does math seem to do such a great job of describing so many diverse systems in the real world. He had the brilliant insight to basically say, screw this. And rather than writing down the Hamiltonian for uranium, he said, well, let me write down a random matrix. And the idea was inspired by statistical mechanics. So imagine a simple world where you have air molecules and they can only move left or right and they all move at the same speed. If you want to figure out a macroscopic quantity like pressure, you would want to figure out how many of these molecules hit the wall in a certain amount of time. All right, well, if you think about what's going on, you have more than a mole is more than 10 to the 23rd objects. This is an incredibly difficult problem to try to write down and solve in closed form. We can't do the computation. So what you do in statistical mechanics is you put a probability distribution on all the possible configurations. For each configuration, you calculate the pressure, and then you average over all configurations. And then, like Wizard of Oz, you click your heels together 3 times and basically pray that most configurations are close to the system average, and that this easy to compute quantity does a really good job of describing what's going on. So Wigner said, let's do the same thing in nuclear physics. Let's choose a large matrix, n by n, choose the matrix entries at random, calculate the eigenvalues, and then do this again and again and again. So we'll have to put some kind of probability distribution on the space of matrices. And there's a lot of reasons as to why you might choose one probability distribution over another. I'm not going to go into all the physics behind this. If people are interested, I'm happy to chat more about this afterwards. But the idea is physics can be described by real symmetric or often complex Hermitian matrices. And these matrices have real eigenvalues. And when you have real eigenvalues, you can talk about the spacings between adjacent eigenvalues. That's the spacings between adjacent energy levels. So a little bit more explicitly, let's imagine we have a real symmetric matrix A. So Aij equals Aji. And we're going to fix a nice probability distribution P. Almost always P will have mean 0, variance 1, and finite higher moments, just so things can converge nicely. There is an entire industry devoted to what are the weakest conditions you can put on P so that everything still converges. And for a lot of things, if like the third plus epsilon moment is finite, then you're good. I'm not going to get into any of those games, just let you know that they exist. We'll define the probability of a matrix A as the product of the probabilities of the matrix elements. And here I'm choosing I less than or equal to j because the matrix is real symmetric. So if I choose this entry here, I know the corresponding entry down here. I don't want to include it twice. We can unwind this a little bit. What does this mean? It means the probability that I choose a matrix where the ijth entry is in some interval alpha ij, beta ij, is just going to be, I integrate my probability for that random variable from alpha ij to beta ij, and I take the product over all the independent entries. Okay, we want to understand the eigenvalues of A. These are going to be the energy levels of our system, but unfortunately, it is the matrix elements that we're given. So does anybody remember a result from linear algebra that relates the eigenvalues of a matrix to the entries of the matrix? I will see if I can see the chat. Anybody has put something there?
Has something to do with the trace, right?
Yes. So when you see this in a linear algebra class, I know when I first saw it, I did not appreciate how valuable this lemma is. And now a year doesn't go by, a summer doesn't go by when I haven't used this extensively. the trace of a matrix is related to the sum of the eigenvalues. So the trace is just the sum of the diagonal entries. And it turns out that similarly, the trace of a to the k is just going to be the sum of the eigenvalues to the kth power. And the trace of a to the k is a polynomial in the matrix elements. This is exactly what we want. It's the matrix elements that we know. But we want the matrix, not elements, but the eigenvalues. If our probability distribution is nice, summing the eigenvalues to the kth power, that's kind of like the kth moment of the eigenvalues. And so it turns out if we can understand these sums for all k, we actually understand the distribution of the eigenvalues. And there are generalizations of the eigenvalue trace lemma in number theory. And we might see a little bit of that later, probably not based on the time. So a little bit more probability notation. So delta x minus x naught stands for unit mass at x naught. So if you want, think of it as the density is 0 everywhere except at x naught where the density is plus infinity. And so we define formally, if I integrate a function that's nice, f of x against the delta point mass, it just returns the value of the function at x naught. So if you want, you think of it again, it's a point mass of size 1 at x naught. If you don't like thinking like this, you could replace delta with a Gaussian with an extremely small variance. And as the variance gets smaller and smaller and smaller, this would converge to becoming a point mass. So these are called approximations to the identity. You can easily revamp it and do it that way. And so now what we can do is to each matrix A, we can attach a probability measure as follows. We take the eigenvalues of A, we divide by 2 square roots of n, and we put a mass of size 1 over n at each of these normalized eigenvalues. And so because there are n eigenvalues in an n by n matrix, this is going to be a probability distribution. So the very first point I mentioned earlier is there's 3 questions, and the first is what is the right scale? So in the 2 square roots of n, which do you think is more important, the 2 or the square roots of n?
Square root of n.
Square root of n. As the matrix grows, as we get larger and larger matrices, this is telling us how do I adjust the matrix? How do I adjust the eigenvalues so I have things that are comparable, that I have things that should hopefully converge in the limit? The 2 is so I can say ellipse, so I can say circle rather than ellipse later. And so what can I do with this? Well, if I want to integrate this from A to B, then we'll just count how many normalized eigenvalues do I have between A and B. The kth moment would just be integrating x to the k against this. And so I get that the kth moment is going to be related to the trace of a to the k over some normalizing factors involving 2's and n's and k's. This is really nice. It means I can calculate the kth moment of my measure just by knowing the trace of a to the k. That involves the matrix elements, which is exactly what we're choosing. And the hope is that we can calculate this for all the different k's, and from that, deduce what's going on about the eigenvalues. So what I want to talk about now, the first statistic is the density of states. So this is, the matrix probability measure we've just talked about. And so Wigner's semicircle law, and it's the first big result in the subject, is if you take n by n real symmetric matrices, choose the entries independent, identically distributed random variables from a nice probability, say mean 0, variance 1, other moments finite, then for almost all A, as n goes to infinity, the normalized measure is converging to the density of a semicircle. And I'll show some pictures of that later. So I want to try to motivate why this is true. So again, the first thing we always need to do is figure out what is the correct scale. So the trace of A squared is going to be the sum of the eigenvalues squared. Well, since these are real, these are all non-negative numbers, there's going to be no cancellation. So if you've seen the central limit theorem basically says if I have a bunch of independent, identically distributed random variables, if I look at the sample mean, that's going to converge to being a Gaussian. If you haven't seen that, it's okay. This is just a quick little motivation. The trace of A squared is the sum of Aij, Aji. It's the sum of Aij squared. Each one of these is drawn from something with mean 0, variance 1. Well, since the mean is 0, aij squared is just the variance because mu is 0, so aij minus 0 squared is just aij squared. So we expect each of these factors here to be of size 1. We have n squared of them, so we expect it to be of size n squared. So the sum of the squares of the eigenvalues should be of size n squared. So n times the average is of size n squared. So the average should be roughly of size square root of n. And this gives us a sense of what is the right normalization factor. It's not a proof, but it at least suggests that normalizing by square root of n is the correct way to go. So now we want to calculate the kth moment. So the kth moment, well, we've already shown it's equal to the trace of divided by some factors. And now what we do is we calculate the average kth moment. So we take the kth moment of our measure, we multiply by the probability we chose that matrix, and then we just integrate over all such matrices. And then the proof proceeds in 2 steps. The first is we show that these average kth moments converge to the moments of the semicircle. And the second is we want some kind of control over variance, some technical conditions to show that most matrices will be close to this. So here is a very misleading calculation or suggestion of how the calculations go. And this case is unfortunately too simple to really highlight the difficulties. If I want to calculate the second moment, that would be the trace of a squared, so it's just the aij squared. And so when I do all the multiplications, well, I take aij squared and I hit it with its corresponding probability, and I have everything else. All of these will just integrate to 1 because it's a probability distribution. This will integrate to 1 because it is the second moment of the variance. I have a factor of n squared from this, divides the n squared over here, so I just get 1/4. Unfortunately, when you try to calculate the higher moments, it becomes a lot more involved. There's a lot more technicalities that come into play. So here is a plot of looking at 500 matrices. I'm choosing the entries from a Gaussian 400 by 400. If you look closely, you'll see that there's a nice solid red line that does a pretty good job of describing what's going on. Now, I could look at the Cauchy distribution. Has anybody here seen the Cauchy distribution before? So this is one of my favorite probability distributions. It actually has a nice antiderivative. It's the arctangent. It's a nice inverse trig problem. What I like about this is it doesn't have a finite variance. If you try to integrate x squared times p of x, well, x squared over 1 plus x squared, that goes to 1 as x gets very large. This is going to blow up. And so the Wigner's semicircle law assumes that you have finite variance, finite higher moments. If you look at what's going on here, it is far from the semicircle. And the stuff you see at the ends, it doesn't just blip up over here. This is just calculating the probability from -300 onward. So it violently does not follow the semicircle. All right, so what we've done so far is we have looked at the set of real symmetric matrices. These are the nicest, easiest ones to work with. What I want to do now is talk about some results I've done with students over the years. And so the first is on real symmetric Toeplitz matrices. It was started with Chris Hammond, who began as an undergraduate at Ohio State and finished as a graduate student at Michigan. And the idea is to look for what I'll call fat, thin families. The family needs to be thin enough so we can see some new behavior. But it has to be fat enough that we can actually do the averaging and do the calculations that arise. And so the first one to look at is the real symmetric matrices that are also Toeplitz. So what does it mean to be Toeplitz? It means it's constant along diagonals. So it's B0 over here, B1 above, B minus 1 down below. If it's real symmetric, then B minus 1 would have to be equal to B1. We might as well assume B0 is 0 if we want, because that just shifts our matrix by B0 times the identity. It shifts all the eigenvalues by B0. This is very different than real symmetric matrices. Real symmetric matrices, you choose the main diagonal and the above, the upper triangular part. That's on the order of n squared over 2 free entries. Here, we only have n minus 1 independent parameters, the different diagonals. So the hope is that we can see some very different behavior. And we're going to normalize the eigenvalues by dividing by the square root of n. So here is a plot of a large number of normalized eigenvalues from Toeplitz matrices. Does anybody recognize this shape?
Henry typed something in the chat. He says it looks like a Gaussian.
It looks like a Gaussian. And so when we were looking at this in the summer of '03, we thought it has to be a Gaussian. And in fact, several people gave us some theoretical justifications as to why it should be a Gaussian. It is not quite a Gaussian. And what was fascinating is it turned out that there was another group that was working on this. And so when I first came up with the results with my students, I started emailing people in the community and I started sending questions all over the world, and eventually got back to me that somebody was working on this 15 minutes from where I was. So it was an amazing game of telephone. And they also thought it was a Gaussian. And it's not quite a Gaussian. It's a little bit too compressed in the center. It's not, doesn't have enough mass going off to infinity. So to just review, we have our measure. We put a size 1 over n at each normalized eigenvalue. I'm going to divide by root n, not 2 root n here. If I want to calculate the kth moment, it's going to be the trace of a to the k over n to the k halves plus 1. It's not too bad to show that all the odd moments vanish and the second moment is just 1. And what we want to do is we want to calculate the even moments. And so when we calculate the even moments, we want to look at the trace of a to the 2k. And so when we expand things out, it just matters what diagonal you're on, because all the spots on the diagonal are the same. So it is a very bad idea to go into technical details during a talk. I am not going to go into all the details that are on the slides. If you want to see more details, by all means, either email me, look at the slides later. It turns out that everything has to be matched in pairs. And the reason is our probability distribution has mean 0. So if any of these elements wasn't matched with something else, it would just be 0. It turns out if there's ever a triple or quadruple matching, there's so few tuples that have that happen that when you divide by n to the k plus 1, it doesn't contribute. So everything has to be matched exactly in pairs. And so we have two possibilities. When we look at the indices, either they're equal or they're opposite. And there's a really nice combinatorial problem. How many ways are there to take 2k objects and match them in pairs? There's 2k minus 1 double factorial, which turns out to be the 2kth moment of the Gaussian. So again, it's a suggestion that the Gaussian might be playing a role here. There's 2 to the k choices of sign. It turns out only one choice of sign matters. And I'm not going to go through the degree of freedom argument, but the only one that works is when they're all matched with negative signs. And so we know that the main term is at most the moment of a Gaussian plus something very, very small. There are 3 possible ways you can match things in pairs. I can match you with your adjacent neighbor like this, or your adjacent neighbor like that. Well, those two are going to be the same. You're just changing your perspective. And then the more interesting one is the diagonal, the crossing. And so there are 3 possibilities. And case 1 is when I match them x1 equals x2. So that's doing this case like this. When you go through it in the calculation, it turns out I1 minus I2 is minus I2 minus I3. So you get I1 equals I3, I2 and I4 are free variables. So you get n squared choices from I2 and I4. You get n choices from I1. That's of size n cubed. And so in the limit, it's going to contribute 1. The more interesting case is when we have the crossing. We now get I1 equals I2 plus I4 minus I3. So you might say, well, we can still choose I2, I4, and I3 freely, but no, we have to make sure that I1 stays between 1 and n, and we're going to lose a positive percent. So for example, if I2 and I4 are both at least 2/3 n, and I3 is less than n thirds, then the resulting sum is going to be greater than n, and that can't happen. So this trivially proves that it's going to contribute a little bit less than 1. And so the third moment of the Gaussian is 3. If each matching contributed equally, you would get 3. It turns out that last one contributes 2/3, you get 2 and 2/3. And so it's not quite a Gaussian. And so what we were able to show is that the limiting spectral measure does converge to something. It is unique. It has unbounded support. It is not the Gaussian, but we can't write down in nice form exactly what its moments are. And that's still an open question almost 20 years later. When you see something that's so close to a Gaussian but not a Gaussian, it suggests we might have asked the wrong question. And so, a year or so afterwards, I was able to prove with 2 other students that if you choose an additional condition, if you make the first row a palindrome, A, B, B, A, one of the greatest groups of all time, that puts in some extra conditions. And now each diagonal except for the main is repeated. When you do that, it fixes these Diophantine obstructions and you now get a perfect Gaussian. All right, so I want to now move on to another very interesting ensemble, the block circulant ensemble. And this is joint with Gene Kopp, who was a graduate student at Michigan until a few years ago when he graduated. And so what we're going to do now is we're going to look at symmetric matrices that are periodic with period M on wrapped diagonals. So here, this is a period 2 matrix, C2, D2, C2, D2, C2, D2, and then it wraps around like this. The advantage of wrapping around like this is now all diagonals have the same length. And that's very beneficial. And so we can try to calculate the details here. So I don't want to go into all the details of this because I want to show you some number theory at the end. It turns out it comes down to, again, how many ways can you do matchings? And it turns out it's related to the number of ways you can match sides on a figure that have certain orientations. And they have to be matched with the opposite orientation. This is then an object from topology that we can then put together. And then you can ask, how many ways can we do it? And it turns out that depending on how many holes your surface has, it contributes a different amount. Turns out that there's an explicit formula due to Herrera and Zagier that has generating functions for this. From this, we can get beautiful relations. We can get moments, a 2kth moment in terms of, again, the Gaussian 2k minus 1 double factorial and this CKM. And again, this was all done by undergraduates. We needed some complex analysis, not a big deal. Took about 1 hour to prove how to do contour integration, which was all that they needed to do. And we can get explicit form. I mentioned different accents. I have the Boston accent. I have the physics accent. There is also the probability accent versus the analyst's accent. So in probability, they talk about the characteristic function rather than the Fourier transform at times. Not a big deal. We can eventually get a nice explicit formula for the density of our function. And so we get it as a function of the periodicity M. And what I love about this is I have a parameter now that I can play with. I can jiggle M. And as I change M, I can see what does that do to the distribution. When you look at this, it may not be immediately clear what is going on. There's a lot of stuff that you can do with special function theory to help analyze this. One of my colleagues and good friends is a physicist. And so he was very well versed with these formulas. And so we brought him on to help interpret them. And so here is a plot of F1. So this is periodic with period 1. So this should be just the palindromic Toeplitz matrices. And you do see that it looks like a Gaussian. And you were only doing 100 matrices. So this is not a very large number in terms of averaging. Our size is only 400 by 400. So it's not a huge size. And already we're seeing a pretty good fit. If we now look at periodic with period 2, you can see it's capturing the bumps. Periodic with period 3, again, capturing the bumps. Period 4, again, you can see how it's going up and down properly. Period 8, and you're already at period 20, we can see that it's getting very, very close to the semicircle, which makes sense because as the period gets longer and longer and longer, it's looking more and more like a real generic, real symmetric matrix. Just putting everything together, you get these beautiful shapes. All right, so what I want to do now for the last thing from random matrix theory, and I'm going to do this fairly quickly, is another interesting ensemble, the checkerboard matrices. And this is joint with at least 3 different students from Michigan, Karsten, Eric, and Finger. And so the initial idea is, if you have a checkerboard, you're used to the black and the white squares. We'll modify it and we'll say every k steps, we will put in a fixed element W. What does this do? Everything else is chosen freely. What impact does this have? And what I like about this is it turns out it creates a little blip over here. And the number of eigenvalues in that blip is of size k. And what's absolutely fascinating is as the matrix gets larger and larger and larger, if we divide by square root of n, it normalizes all but those k eigenvalues to be roughly between -1 and 1. But these eigenvalues will be of size square root of n. Even though there's very few of them, when you try to calculate things with moments, those small things will completely dwarf all the others. So even though we have n-5 eigenvalues here, the 5 eigenvalues here, as you start calculating the third moment, the fourth moment, will overwhelm and you won't be able to see anything. So the real challenge for this project was to figure out how do we focus on just what's going on in the blip or just what's going on in the bulk. And the next few pictures just show you as we increase the size of the matrix, you can see the blip moving slowly off to infinity. So the solution was to choose a really nice weight function. And so the function we chose was x to the 2n, x minus 2 to the 2n. So most of the eigenvalues should be between 0 or 1 if we normalize not by square root of n, but by n. So if we normalize by n, the blip eigenvalues are now size 1. The other ones in the bulk are of size 0. And so if you look at this, the probability it assigns to anything that's not near 1 is essentially 0. Now, yes, if we get very far below 0 or above 2, it starts assigning a large probability. But fortunately, none of our eigenvalues are going to be that far away from 0 or 2. And just zooming in, you're looking at n equals 4 to the m going from m equals 0 to 5, you can see how this function is getting tighter and tighter and tighter, so that if you're any distance away from 1, there's essentially no contribution. And so this allows us to localize and study what's going on in a very small neighborhood of 1. And it turns out that we can study these blip eigenvalues very well. And it turns out that there is beautiful formulas for what goes on. It's just like small k by k real symmetric matrices that are 0 along the main diagonal. All right, so this was classical random matrix theory. These are looking at different ensembles of matrices. The motivation for this is that we believe that this describes things like uranium, like heavy nuclei. It turns out that there are connections between number theory, nuclear physics, and the like. And so in the 1970s, Montgomery, professor at Michigan, was visiting the Institute for Advanced Study. Is he on the call right now? Otherwise, I've got to be very careful how I tell the story. Okay.
I don't see him.
Okay, so when he was visiting the Institute, he was talking to the great mathematical physicist Freeman Dyson, and Dyson was asking, so can you tell me what you're looking at? And so he was talking about some things he was looking at distributions of zeros of the Riemann zeta function. And when he wrote down what he was seeing, Dyson said, that's amazing. We see the same thing in random matrix theory. We see something similar when we look at nuclear. Tweaking the story a little bit, but essentially the same stuff was showing in different places. And it turns out that these ideas from random matrix theory can model things in number theory. So what can they model? They can model L functions. So let me talk to you a little bit about L functions. So the most important is the Riemann zeta function. So it's defined as the sum of 1 over n to the s, where n ranges over all the integers. And it turns out, using the fundamental theorem of arithmetic, this is the same as the product over primes of 1 minus 1 over p to the s inverse. So you basically just use unique factorization. Any integer can be written uniquely as a product of prime powers in increasing order. Use the geometric series to expand each one of these and just multiply it out. The reason this is so wonderful is because there is no mystery in the integers. Can anybody give me a formula for the nth integer? F of n equals
n.
F of n equals n. What about spacings between adjacent integers? The spacing between adjacent integers is?
We see lots of ones. Lots of
There's no mystery at all. This is very different than primes. If I ask you, what's the next prime after 2020 and what's the next prime after that? Much harder. So for example, here's some applications of knowledge of the sum over integers and how we can pass that to knowledge of the product of the primes. And if you're thinking that there's a connection between this and the eigenvalue trace lemma, morally, yes, it's the same idea. Is we want to connect from something we can understand to something we want to understand. So we're going to look at two different values. These are called special value proofs. If we take the limit as s goes to 1 from above, well, this becomes the harmonic series, the sum of 1 over n, which diverges. If there were only finitely many primes, this product would converge. Therefore, there must be infinitely many primes. So the number of primes less than or equal to x has to go to infinity. If you do a little bit more work, you can even get some kind of growth rate, and you can show that there's so many primes that the sum of their reciprocals diverge, which is a lot more than the squares. The sum of the reciprocals of the squares converge. Well, speaking of squares, if I take s equals 2, this is the Basel problem. The sum of 1 over n squared is pi squared over 6. What kind of number is pi squared?
Irrational.
Irrational. If there were only finitely many primes, well, when s equals 2, each term in the product is a rational number. If there's only finitely many primes, their product would be rational. Therefore, there are infinitely many primes. Now, unlike Euclid's proof and unlike the s equals 1 proof, it initially doesn't give you any information about how quickly does the number of primes go to infinity. And so when I was a postdoc at Brown, this bothered me enough that I decided to see, could I get some kind of growth rate? And I was able to prove that the number of primes up to x is at least log x by knowing something about how irrational pi squared was. This is the worst theorem I ever proved in my life. Now, you might think it's a terrible theorem because if you use Euclid's method, that the number of, to prove the infinitude of primes, Euclid gives you log x. I'm getting log x. That's not why my method, that's not why my result is bad. My result is bad because the way you prove things about how irrational pi squared over 6 is you need to know that the number of primes up to x is x over log x. So by assuming there's x over log x primes up to x, I can prove that there's log x primes up to x. Well, there's faster and better ways to do this. The reason I'm sharing this story is it's a great warning of how careful you have to be to make sure you are not assuming something in your arguments that you shouldn't. I then opened up the argument with some of my students, and we were able to extend this and actually get a good result at the end. All right, so it turns out that initially it's defined only for the real part of s greater than 1, but we can extend it to a function that's defined for all values of s. And the Riemann hypothesis is that all the non-trivial zeros have real part 1/2. That means we can write the zeros as 1/2 plus I gamma. It means we can talk about spacings between the adjacent zeros. And this is very similar to what we were doing with matrices or the energy levels. Instead of looking at the Riemann zeta function, you can look more generally at an L function where we replace the 1 with some coefficients. And we always want to choose things such that we have a product. And there's a lot of good reasons from complex analysis as to why you would want to do that. And we believe that the generalized Riemann hypothesis is true, that they will all have real part 1/2 for their zeros, and then we have similar gains. So over here is a spacings between thorium. There's 227. I believe that this was inputted with the help of one of my friends who is now a professor of physics at Michigan, back when I was doing my thesis. And this just shows you the paucity of data we have on the physics setting relative to the number field setting. On the number field setting, here's 70 million zeros of the Riemann zeta function starting at the 10 to the 20th zero. And you see this phenomenal fit between the random matrix theory predictions and the observations of the zeros. There really is something to the story about how they correspond to each other. What you can do now is you can try to look at other quantities. So look at curves of the form of y squared is x squared plus ax plus b. And it turns out that there's going to be a rational group. There's going to be a group on the rational solutions to this. So if P and Q are 2 points that have rational coordinates, if you draw the line connecting them, that line will have a rational slope. It will intersect the curve in another point. And if you reflect it and define P plus Q to be this reflected point, it turns out you get a abelian commutative group. And you can use this to form an L function where these coefficients are going to be related to the number of solutions mod p. There's a lot of wonderful questions you can ask, and one of them is the famous Birch-Swinnerton-Dyer conjecture, that the group of rational solutions, the rank of that is equal to the order of the L function vanishing at 1/2. So there's a lot of technical things you can go into. I don't really want to go into too much detail, but there's a lot of questions in number theory that turn out to be related to the properties of zeros of L functions. So understanding zeros of L functions is extremely important. I'm going to skip a little bit. I want to give you a quick example of, if you know a little bit of complex analysis, how do we get these connections? So one of the things you always want to do in complex analysis is integrate the logarithmic derivative. So if I take the derivative of the log of a function, I'll get zeta prime over zeta. And when you do contour integrals of that, that gives you tremendous information about the function. You can now see why we want an Euler product. Instead of writing my function as a sum, if I write it as a product, the log of a product is the sum of the logs. Oh, I can now differentiate term by term. I can expand things using the geometric series formula. And now when I do my integration, it turns out I only have to really worry about the main term. And this is essentially the analog of the eigenvalue trace formula. And so I'm not going to go through all the different details there. It turns out if you want to try to model what's going on with zeros of elliptic curve L functions, there are some issues initially. Here is a histogram of the results, and here are some solid theoretical curves that are having some trouble. But if we adjust our model a little bit, and we take into account various discretizations that happen, it turns out we get a. And so for the last slide, I want to just give you a little bit of a conversion factor from physics language to number theory language. So in number theory, we study the zeros of L functions. In nuclear physics, we study the energy levels of heavy nuclei. How do we get information on the energy levels? We shoot in a neutron. And when we shoot in a neutron, we look at what comes out. In number theory, we shoot in a Schwartz test function. So what is that? Well, if we go back over here, when I do my contour integration, I integrate against x to the s over s, and it turns out that this integral on this side becomes an integral over primes. And so if I understand what's going on with primes, I can understand what's going on with the zeros of the L function. Instead of hitting it by x to the s over s, I could hit it more generally against some nice function phi. And so I would have an integral of phi against p to the s. Well, I can write p to the negative s as e to the negative sigma plus it log. And what you might notice is, oh, this is essentially the Fourier transform of something related to phi. And so over here, I have a calculation involving zeros of my function and my test function phi evaluated at the zeros when I do my contour shift. And over here, I have my function, the Fourier transform at the primes. And so the neutron, its role is played by a Schwartz test function. We would love to be able to shoot a neutron of arbitrary energy into the nucleus. If we could do that, we could understand everything. In number theory, we would love to have a test function that is essentially the Dirac delta, the unit point mass. And then we would know exactly what's going on at one point. Unfortunately, the sums that arise, the sums over primes, we can't do them if the test function is arbitrary. We can only do it if it has suitably restricted support. And so this is the language that allows us to convert from number theory to nuclear physics or nuclear physics to number theory. There is an analog. As a nice aside, if you are familiar with the uncertainty principle from quantum mechanics, it is actually just a statement about a function and its Fourier transform. So there is a rich history of physics and mathematics inspiring each other. And so all of the stuff I talked about today, except for the elliptic curves at the very end, which was done with some undergraduates and some graduate students, was all done with students, most from Michigan at some point, a lot of them only knowing basic probability and a little bit of linear algebra when they began. The real challenge is coming up with what is going to be interesting, what's going to have behavior. And what I love is a lot of the stuff, including what Fengu did last summer, on the generalization of the checkerboard, it was the students who came up with what we should study. So there's a lot of opportunities for creativity here. And again, the deadline for the Williams small RU is February 3rd. The Polymath Junior, which I'll just say a few words about quickly. We started this last year because we were concerned about how many students were losing opportunities because of the pandemic. And so we accepted anybody who applied who had taken at least one theory and had at least one professor who wrote a letter of recommendation for them. So we had about 300 students working in 12 groups. And so the idea, very similar to these massive online programs, is to provide a tremendous number of opportunities. You will notice that the deadline for this is much later than the deadline for most of the standard REUs. This is deliberately so that if you get into a standard REU, wonderful, hopefully do that, hopefully in person. But if not, we are going to hopefully try to take as many students as we can again this summer. We will hopefully have a diverse list of topics and mentors. I think we already have 12 people committed already. And then happy to stay on and chat a little bit more. So thank you.
All right,